So this is the second last video in the rotational motion topic. In this video we will be looking at work and power in rotational motion. So the relationship between torque, work and power. So this is a very short video, and I had originally had it as part of the previous video. However, I figured it was probably nicer to split it up and give you a chance to have a go at a larger number of practice questions. So all we're doing in this video is translating our linear equations for work and power into rotational variables. So under translational motion, we know that our work is equal to our change in kinetic energy, which is the final minus the initial kinetic energy. We know that our work is equal to the integral of our force over the displacement, and we know that our power is given by the rate of change of our work, which is also equal to the force times the velocity. So in rotational motion, we know that our kinetic energy is equal to half times the rotational inertia times our angular velocity squared. So substituting that into the translational motion equation, and we find that the work done by a rotating object is equal to half times the rotational inertia times the final angular velocity squared minus the initial angular velocity squared. So it is the exact equivalent of how we find work in our linear motion. So our second equation, the integral of the force, becomes the integral of the torque. We know that our linear variable, the displacement, is equivalent to our angular variable, the angular displacement d theta. So although torque is not a force, it is the rotational equivalent. The torque is the rotational consequence of an applied linear force. So integrating, assuming that we have a constant torque, then we get that our work is equal to the torque times our angular displacement, theta f minus theta I. And our final equation for the power, our power is equal to the change in work over time. So taking this second equation for the work, we find that our power is equal to the rate of change of our torque times our angular displacement. For a constant torque, that gives us that we are depending on the rate of change of our angular displacement, which gives us that our power is equal to the torque times our angular velocity. So as I said, this is a very short video. This is the second last video in rotational motion, and as you've probably realized by now, the bulk of the work in the rotational motion is just remembering how our linear equations translate into rotational variables and untangling the questions.